Ornith 1, this is a new class of open weight models which are blowing up at the moment. Now, a lot of people are talking about benchmarks. This is specifically designed for agentic coding, and it actually shows up in the performance. So a 35 billion parameter model is able to outperform a 10 times bigger model on terminal bench. And the story holds up for the rest of the benchmarks if that's something you are interested in. Now, we have a very similar story for the 9 billion parameter model. Again, it's able to outperform 3 to 4 times bigger open weight models. But that's not the interesting thing here. The interesting thing is that purpose-built open weight models are finally catching up to closed source models. So the bigger 397 billion parameter model is very close to Opus 4.8. However, it's not about the benchmarks. It's how this specific family of model is trained. So in the last few years, we have seen that open weight models have started to catch up to closed source models. Ornith 1 series follows the same trend. But more importantly, with this, the company behind the model, Deep Reinforce, shows how to train a specialized open weight model that can beat the base model it's trained on top. Okay, so why I'm making this video and what makes this model special? So there are two different things which I want to highlight. First, the way these models are trained is very different. And during training, Ornith learns to generate both the solution rollouts for a given prompt and also a task-specific harness that guides those rollouts. So it doesn't just write the solution, it writes the harness that guides it. And both are trained together in a single loop. Okay, before showing you how exactly it writes its own harness, one thing to highlight. This is not a completely new model. It uses existing pre-trained bases, including Qwen 3.5 and Gemma 4, depending on the size that we are looking at. Then they keep training them with their own reinforcement learning technique, which we're going to look at in a minute because that is the most interesting part here. Now, the beauty is that since it's using an existing base model, you can directly compare this new Ornith model with base, and you can actually see what type of performance gain you can get out of this new model. Okay, so let's talk about this idea of custom harnesses that the model is able to generate for every task. So the harness around the model is basically the loop. It has its own memory, tools, retries, and error handling. So normally, so far that we have seen that a human writes these harnesses by hand, specifically designed for every model. Now with Ornith, the model writes this harness loop for itself based on the complexity of the task. Now this idea is very important because this is basically task-specific harness, which is not built in stone. The model is able to create one on the fly, ensure that it's able to solve the problem, and then discard it if it doesn't need it. In a way, you can say that this is basically self-improvement on the fly. So for every given task, the model writes the scaffold for the task. Then it solves the task inside that scaffold a few times. Those are basically the rollouts we talked about. So it will generate multiple different solutions based on the task-specific scaffold or harness that it created. And then for each one of them, it will try to solve those based on those trajectories. Now, each attempt gets scored. So there is basically on the fly reward. And then here's the key. The reward updates both the solution and the scaffold that it produced. So it uses the GRPO, which just means do more of what scored well. So good harnesses emerges on their own. Now, if the model designs the harness and takes the test, a problem you can think about is whether it's going to take shortcuts. This is the problem of reward hacking. So it could read the hidden test, hardcode the expected output, or copy a solution that it knows is already there. We have seen this behavior with some of the proprietary or frontier models, even with GPT 5.6 that was released today, the meter folks found that the model tend to cheat. And if it does that, it's going to get full marks without learning anything. This is a classical example of reward hacking. And it's what kills the naive version of this whole idea. So the researchers had to really think about it and make sure that they create defenses around reward hacking during the training phase. All right, so let's talk about those different ideas. So they stopped it in 3 different layers. First is the locked boundary. The environment, tools, and tests are fixed. The model only edits the inner scaffold. The second is a deterministic monitor. If it reads a hidden file or touches the grader, that attempt gets a 0. And the third is a frozen model acting as a judge, which can veto a run even if it passed. So you have got 3 different guardrails stacked around the model that are purpose built. And the idea is that it's going to behave as a wall, a rule checker, and a judge that is going to hopefully negate reward hacking. Okay, so this is all of this actually help. I want to actually test this. So I ran some of my own tests with Ollama. I'm using the 8-bit quant on the M2 Max. And in this test, I put the 9 billion model, both the base versus the post-train Ornith 9B. Okay, so the idea was there are 3 different sets of tests. One is plain coding, harness creation, and the behavioral long horizon stuff. In this case, I ran it on the same prompts, same token budget, and I also read the transcripts to see what exactly these models were producing. Now, these tests were inspired by Tom Turney. He actually ran the tests on a bigger 35 billion models. That's probably the one that we want to use, but based on the machine that I have right now and the resources that are available, I decided to run the smaller 9 billion model. And this is where you actually see the differences between the bigger 35B versus the 9B. And also, this I think gives you a signal of don't just try the smaller models because they may not be following the trend. Okay, so here are the results on my private bench. There are 2 different sets. One is objective coding. There are 8 tasks. I'm just showing a few of those here. And then harness creation, another 4 tasks. Now on accuracy, they are pretty close. Ornith 9B gets 6 out of 8 versus Qwen 3.5 9B base gets 7 out of 8. And interestingly, they get the same answers. But the thing that I found here was the efficiency. The Ornith 1 9 billion model is a lot more efficient compared to the Qwen base version. We are looking at pretty substantial difference depending on the nature of the task. Now, across the board, you get comparable accuracy, but Ornith gets there roughly 3 times cheaper. Now, in this post from Tom Turney, he actually ran an interesting test that I wanted to replicate with this 9 billion model. So in here, he says that a long horizon is where it matters for agentic coding. He injected a false claim mid-conversation where the user was insisting that we decided on Redis, which was actually not what happened. And in his tests, Qwen seems to completely miss that, whereas Ornith caught it. It was not deceived by this poison. Okay, now I tried to replicate exactly the same scenario here. However, both the base model and this post-trained Ornith 1 9 billion model actually confidently got this wrong, and they didn't capture the lie that was introduced, right? I was hoping that we were going to see a similar behavior in the 9 billion model, but it seems like it's not as smart as the 35 billion model. So the actual difference that you are going to start seeing between the base model and this post-trained Ornith 1.0 model is probably going to be around 35 billion or the bigger, almost 400 billion model. Okay, so a couple of findings for that 9 billion model that I actually tested. For this case, a capability is about as same as the base model from which you basically start. However, the real win that you see here is efficiency, which is roughly 3 times cheaper. And on some tasks, it's up to 20 times on single tasks, which is kind of pretty incredible if you want to run these as workhorse models. If you want them to stay honest under pressure, you probably need scale. As I mentioned, that 35 billion model is showing a lot more intelligence compared to the 9 billion model that I tested. And that's, I think, what most of the people are focusing on when they are talking about Ornith 1.0 model. Okay, so towards the end of the video, I do want to share a few caveats that probably is going to be different when you try to test it. So this was first a 8-bit quantized model, not the full 16-bit. Now, keep in mind, I tested both the models in 8-bit quantized to make sure that the comparison is fair. However, there might be some configurations which are going to be impacting it. I didn't really try to optimize for that. And these are a handful of tasks on a single run. So treat this as a smell test, not a benchmark, because you probably want to run them multiple different times, which I'll probably do with the bigger model, which when I have enough compute. But I'm mainly interested in how they were able to train the model, and we were going to probably start seeing more and more of these task-specific harnesses that the agents can build on the fly for themselves. Talking about task-specific harnesses, I think Anthropic dynamic workflow is a really good example of this, where you can use an agent to build harnesses on the fly. But I think it would be interesting to see if we can actually see similar patterns from open weight models as well. All right, do let me know if you get a chance to play with the model, what your experience is. Is it different than what I had with it? Anyways, I hope you found this video useful. Thanks for watching, and as always, see you in the next one.